So now, after going over section 4.1, which is the general exponential functions, we're going to talk about very specific exponential functions, those that have a base e. So exponential functions to the base e. Remember, e is built into your calculator. If you forgot from 1150, there's two e's in there. There's second division sign, it will just give e, and then hit enter, it gives you the value of e. And there's the e with a power, like if you do second ln, which is next to 4, gives you e with a power. And then say you want to do e to the first power, which is e, or e to the second power, you can do it again, and so on. So e is roughly 2.7. It's an irrational number. It has a non-terminating, non-repeating decimals. Okay, so e repeating decimals, it's roughly 2.718. And in my notes, I show you it where you can do it in your calculator, and it shows you where e came from. Like if you put the expression 1 plus 1 over n to the power n in your calculator, or 1 plus 1 over x to the power x, it doesn't matter. So let's delete what's in there. So if you do parentheses 1 plus 1 divided by x, right parentheses to the power x, and go to table, and then key in, increase the value of n, like make n 10, and then 100, and then 1,000. As you can see, as n 100,000, as n increases without bound, that number that you're looking at, it's starting to converge to 2.718. So let's put 1,000,000, and that's 100 million. So you can see, and if you want to see how more digits, go up and then highlight that number. It shows you a lot more digits, and it only shows you this many, but this never ends. So that's where e came from. So e is 1 plus 1 over n to the power n, as n increases without large, as n goes to infinity. Okay, that's where e came from, and it turns out to be roughly that number. All right, so now, so since e is a number which is roughly between 2 and 3, 2.7, if I want to graph y equals e to the x, exponential function to the base e, right? Exponential functions to the base e. If I want to graph this, remember the basic graph of exponential functions? Is it going to look like where the base is between 0 and 1 or greater than 1? Since e is greater than 1, the graph is going to look like this. If you make a t-chart, that's what you're going to get. If you put it in your grapher, that's what you're going to get. Look. Y equals e second ln to the power x, and then graph. Bingo, it's exactly what we thought it would be. It's an example of exponential growth. If you do e to the negative x, e to the negative x, it's gonna a base of almost 1/3, 1 over 2.7. It's gonna look like the exponential decay that we know of. Okay? Because of the base. So e to the x is example of exponential growth, and e to the negative x is an example of exponential decay. Okay? Because remember, this is 1 over e to the x, which is a base between 0 and 1. So let's look at page 341, number 8. Page 341, number 8. It says graph the function by plotting point, not by plotting points, but using the basic graph, and then state domain, range, and asymptote. So number 8, how do we graph y equals e to the negative x minus 3? So you can see it's going to be exponential decay, shifted 3 units down. So it's going to be that, but shifted 3 units down. So we're starting with the y-intercept. 0, 1 is going to go down to 1, 2, 3, 0, negative 2. The x-axis, the asymptote, is going to go down to y equals negative 3. And then copy and paste. And that would be the graph that we're looking for, y equals e to the negative x minus 3. All right, let's look at 12 from that same page. F of x equals negative e to the negative x. So it's e to the negative x, which is dk. We reflected in the x-axis. So it's the dk reflected in the x-axis, so it'll be this, 0, negative 1. Okay? And then number 16, page 341, g of x equals negative e to the x minus 1 minus 2. So it's e to the x, which is growth. It's going to be shifted right 1 unit, then flip, down 2. So shifted 1 unit to the right. So it's e to the x. Shifted 1 unit to the right. Instead of 0, 1, it will be 1, 1. 1 unit to the right, and then flipped. So it'll be down here. And then 2 units down. So it'll be at negative 3, 1, negative 3. And okay, so let me just make sure we all understand this. This is the original function, e to the x. It has asymptote y equals 0, intercept that. If we shift it 1 unit to the right, you will have that. This is e to the x minus 1. You flip it. This is negative e to the x minus 1. Then you go down 3, down 2. So, so you go down 2, so you're about here, and it's gonna be same graph. So the down 2, y equals negative 2, so you're gonna get this graph. Y equals negative e to the x minus 1 minus 2. So this is the final outcome. All right, so remember we did consider compoundings in the previous session, and we talked about monthly compoundings, quarterly, semi-annually, daily, and so on. What if we have continuous compoundings? What if the interest is added all the time to your account? Every time you refresh your screen, your balance changes. Continuous compoundings. So how many times is the interest added to your account per year? A lot. So basically n is infinity in this case. So when n is infinity, I couldn't possibly use this formula anymore, because how am I going to put infinity in there? It's not something that we can just plug in. Okay, it's not something that we could just plug in. Okay, so when it's continuous compoundings, meaning the interest is added to your account all the time as in infinite, so we cannot use this formula. Remember what we said? 1 plus 1 over n to the n is e if n is infinite. We do have n infinity, so this part is going to go to e, and we need an r. If we put an r here, so it's an r there. If we put a t in the power, so we have a t in the power. If we timed it by p, so we get Pert. So when do we use Pert? If interest is continuously compounded. Again, this formula is at the bottom of the slide right there. You use amount equals principal e to the RT. This is only used for what? Continuous compounding. For any other compounding, you use the top. For continuous, you use the bottom. Continuous, everything else. So 34, page 343. 34, page 343. It says if $3,500 is invested at a rate of 6.25% per year compounded continuously, find the value after 3 years. I'll do part A. So it says continuous compounded, so that's how I know this is the formula. The principal is 3,500. E is E. The rate is 6.25%, 0.0625. And the time is 3 years. So I'm gonna put that in my calculator the way it is. So 3,500 e to the power 0.0625 times 3, right parentheses, and that would have be $4,221.81. $4,221.81. Okay, 38. Which of the given interest rates and compounding periods would provide the better investment? So you have 5 and 1/8% per year, compounded semi-annually. In part B, we have 5% per year compounded continuously. So they're not telling us how much to invest, so you can take any principal you want. I'll just for simplicity, I'll do 10 grand, so I can put a number in there, okay? So for the first one, I'll use P into 1 plus R over N and T, and this is continuous, so use Pert, okay? So 10 grand, 1 plus, the rate is 5 and 1/8, so it's 0.05125, right? 5, so it's 5.125%. If you move the decimal 2 places to the left, that's what you get. N is twice a year, and then 2 times the number of years. Just use 1 year, okay? T is 1 for both of them. And over here, it's 10,000. You can use any number of years. E 0.05 times 1. So if you put that in your calculator, each one of them, 1,000 to 1 plus 0.05125 divided by 2 to the power 2 times 1. That one gives me $10,519.07. Let's see the continuous one. 10,000 e to the power 0.05 times 1 gives me 10,512.71. So this is better because the rate is higher, okay? Okay, that's all I wanted to do from this section. It's pretty short section. So until 4.3, have a good night.